application cellulose nanofiber in the composite, that is styrene and butyl acrylate copolymer latex they have used. And nowadays you will be seeing that a lot of cosmetic application, you will be seeing that we will use the cellulose nanofiber as a thickening agent instead of the basically that your hydrogen bonded polymeric material which has a very good hydrogen bonding, people used to use as a thickening agent. But over a period of time, that you must be knowing, the microplastic is a really issue, that for the remove the microplastic issue in the water media, that people are just encouraging to utilize the cellulose based thickening agent for the that cosmetic application. 2021 first pilot plant in India, first pilot plant in the Sweden, Stockholm, and then in India basically the first pilot plant has been established in 2015 in Mumbai. And definitely there are so many different applications and aspects to utilize this particular material, that if you see that there is a huge market, it is keep on growing to its application end. There are many industries, those who are working in the particular cellulose nanofiber area. There are so many academies, there are so many government agencies, they are working. And in India, what I told you earlier itself, Circuit Mumbai, they have the pilot plant, but unfortunately, till date, whatever I do have some connection with them, they are not able to come up with a very good production level. There are lot many issues to getting this thing due to some other issues related to production level. They are not come up with that at a very good level. And I'm fortunate that I was associated with that of the nanocellulose vehicle project in Kyoto University, because I was a GSPS fellow in the Kyoto University in collaboration with Toyota Motors. And most important thing is that whatever you are seeing it here, this particular car structure, this is almost 70% is made of the cellulose or cellulose derivative after its use, except engine and tire and some parts where polymer cannot be utilized, only metallic part can be utilized or other material will be utilized. Almost 70% polymer has been replaced with that of the cellulose material or cellulose derivative. And as a result, what happened? They are targeting. This is the next generation project for the car, and it will be reducing the extraordinary amount of carbon dioxide, and it will be very, very light in weight. Then, as a result of what happened, that it will be very, very fuel economy. So they have already showcased during the Olympic 2020, and I was very fortunate that I was the part of this thing for the thermal insulation of the car cabin. And it is very interesting to work with them for the super thermal insulation by the aerogel with that of the made of the cellulose material. I'll be telling a little bit of that particular that also. So this is the skeletal structure. So I'm not showing all the things because due to the misclassified item by them. Okay, and why nanocellulose? Why we will be using nanocellulose as material for our application? Because there are now it's very, very high strength. Mechanical properties is more than 3 gigapascal in the nano level. We do have the simulation, and we have checked with the atomic force microscope that it is very, very high strength. Fiber-like structure, high crystallinity, low density, thixotropic behavior. What you are seeing it here, then more reactivity due to the presence of OH group, that you have the tuning point to do any modification. After the modification, what you want to utilize as a functional group of this particular material, you can utilize it. High surface area because it's nano. As this is the originate from the plant, it is biocompatible and non-toxic. Definitely, it's must be biodegradable and abundant and renewable. All those things, it's help us to make a comment that material from the forest will save our world. So if I compare the material characteristics with the mechanical point of view, if you see tensile strength, we are very much higher than that of the specific tensile strength I'm talking about. You are much higher than the carbon fiber or the other stainless steel. And if you see, it is stronger than steel, stiffer than aluminum, cellulose nanocrystal, what I told you, 7.5 GPa, cellulose nanofiber, generally 3 GPa we use to get the tensile strength. And modulus value, you can realize 145, whereas that your carbon nanotube, it has a very good tensile strength and tensile modulus also. But I'll be telling in different aspects why cellulose nanocrystal is more important than the cellulose carbon nanotube or nanofiber. If I compare with the other material like your graphite, fume silica, e-paper, surface area is almost very, very high, then we can utilize for the minimum amount can help us. The relative comparison with the other material, if you see that your high strength, the glass, high strength steel, density is very, very high. Tensile strength is 600 megapascals. Whatever we are getting, cellulose nanocrystal, it is huge, 7.5 GPa. So you can realize that this material can be utilized for the reinforcement of the polymer matrix or other matrices to replace that type of mechanical, to replace or compete with that of the metallic material itself. Now, just if I compare, though I have told you related to the carbon, that competitive material of the cellulose nanofiber and cellulose nanocrystal, competitive materials, carbon nanotube, single wall carbon nanotube, multi-wall nanotube. Yes, we are nowhere with that of the mechanical point of view, with that of the carbon nanotube and cellulose nanofiber, carbon nanotube is very much high. Or if I compare with the carbon graphene material, again, it is very, very high. Now, just if you see the comparison, tensile strength, 2 to 6 GPa, and whereas we are getting for the CNT, then 11 to 63 sometimes. The Young modulus, again, it is TPa, then it is very, very high. Conductivity, there is no conductor cellulose nanomaterial, but there is a conductivity. Optical property, it is transparent film, that it is not transparent. But yes, from that point of view, you're supposed to make a conclusion. We're supposed to use the carbon nanotube than the cellulose nanocrystal. But now, if I compare the manufacturing point of view, you see that manufacturing point of view, what is the energy requirement? Energy requirement is 500 to 2,300 kilowatt hour per time. So if you see it, you cannot realize it's 278,000 or 250,200,000 watt. It's huge energy is required to just manufacturing the carbon nanotube that compared to the carbon nanofiber, cellulose nanofiber, and source is fossil fuel. Here source is abundantly available with that of the material for this material, and cost wise it is very, very cheap, and it is, you see, it is very, very high in cost. Major application, there are so many different applications, packaging, food packaging, wound dressing, all the things, and here definitely electronics and all the things we used to use. But most important parameter, I want to just tell you that after disposable, our material will not create any problem to the environment. Rather, the material, whatever you will be using during its application as well as during its disposal, it is not degradable at all. That's why health hazard as well as the pollution to the world, it will be very, very high than that of our material. So wherever there is a requirement not to replace the carbon cellulose carbon nanotube, then definitely we will be using the carbon nanotube. But if it's a lower limit of the material, lower limit of the mechanical properties required, then yes, easily we can replace, because in the BMW car and all the things we used to use the graphene or carbon nanotube or carbon nanofiber, that we are targeting to utilize this particular replacement with this particular material by cellulose nanofiber. So, hello, I'm not able to.
Yes, sir, you're audible.
But my slide is not moving. Okay, now it is moving. Okay. So different utilization of cellulose nanofiber. So what I told you, we can utilize as a cellulose nano reinforcement, and biomedical application also. Nano paper we have developed for the packaging application in the display system, that also can be converted. We are working on with that of the cellulose nanofiber film for this display application also. Flexible substrate, what I told you, cellulose aerogel we have already developed. I'll be telling either it has a mechanical properties very good, thermal insulation is very good, we can utilize for the different application. I'll be telling to you, and it's three-dimensional porous structure. Due to three-dimensional porous structure, just if you see, it is very, very high in strength, but it has a porosity is almost 98%. So we can utilize for the some other application, oil water separation. I'll be telling slowly for some other that particular things. So various production methods. That mechanical method is the homogenizer, microfluidizer, ultrasonication, refining, grinding, cryocrushing. People used to use either chemical method. People used to use the basically acid hydrolysis or alkali treatment. But our thought process, basically, it is a little different. Whatever I am showing it here, it is very high energy consumption. And it's if you see comparison with that other acid, whatever people have used, we have used a little bit of different way, that we will be using the pre-treatment process by alkali and other material, so that you will be getting the minimum energy. Sonication energy we have calculated is very, very less than that of the reported value itself. This is the extraction procedure we have adopted. Instead of the TMPA process, whatever it is available in the abundantly available, whatever it is available in the literature. Not only that, people used to use the strong acid hydrolysis for this cellulose nanofiber extraction, but here I'm not utilizing that type of things. I'm using acidified sodium chloride, which is a delignification agent and which is the major important part of this extraction things. Then I'll be telling just how we have utilized it. This is the process: first dewaxing, fiber soaking, then acidified sodium chloride treatment, then hollow cellulose, followed by treatment of 4% of KOH. This is the removal of the hemicellulose, all the things, it will be removed. Then all the things, whatever we will be getting after centrifuge, we'll be getting the cellulose nanofiber. I'll be showing the characterization things, all the things, so that you can realize, because this particular FDP, whatever I have realized, it is the new material with the new adverse characterization. Also, I'll be telling the all characterization things, and during that time, I'll be telling what is the principle behind it also. This is the mechanism. First, we have done the succinate acidified sodium chloride that used to generate the chlorous acid, which is strong oxidative agent. And this oxidative agent, this is the lignification, delignification agent. And lignin used to present, there are different type of lignin based on the source of the biomaterial, whatever you have used. Based on this thing, we will be getting different type of lignin removal. And here, most important thing, again, I am telling to you, lignin has a very good calorific value. In the paper industry, what they used to do, they used to use this lignin as a fuel in the, basically they are for burning to getting the energy. But our thought process, why to utilize this as a fuel, resources of energy. Rather, we can reutilize this material, we can make a derivative of the lignin derivative. And there are so many numerous applications like this. Recently, we have started working with the lignin-based resin for the tire industry, which can reduce enormous amount of carbon black that has been used for the reinforcement. Lignin modified material can be utilized at the 10% or 5%, that can reduce almost some 30% pH, 30 pH of carbon black in the mainline production of the tire. So we are targeting like that way to whatever we are getting, that's supposed not to be waste. And another thing, during the process, extraction process, though a majority of the raw material, whatever we have handle till date, it is less amount of silica. But whenever we are targeting with that of the you must be knowing, in the northern part of the country where I'm staying, that there is a lot of air pollution due to staple burning, like that rice straw and wheat straw they used to burn in the field itself, and it is creating the problem not only to the soil but also to the environment. So we are targeting to utilize, because we have a one NBCC project to utilize this particular material from the construction application. We are targeting to get the silica, nano silica. Definitely we'll be getting the cellulose nanofiber out of it. That is sure. We'll be getting the lignin. And next, whatever we are targeting, that is the nano silica material that can be utilized for the different medical application. And I think if we have come up with a good application oriented things, then it will be very beneficial to the society itself. And this process, whatever I have adopted, we are getting the very good pulp strength, which is very important for this application of this particular material. If you see the tempo oxidized process, whatever people are reported already that it is a little bit different, and that's why pulp strength is a little different, whatever they have reported. So that already we have patented this technology and published also. Then if you are interested, then I can give you all the details to this thing. This is the mechanism, acidified sodium chloride. What happened, it will be just a delignifying agent. And finally, alkali treatment, we'll be getting this all renewable of the hemicellulose. And after ultrasonication, we'll be getting some crystallized and crystal domain and amorphous domain. And if we able to just remove the amorphous domain, then we'll be getting the cellulose nanocrystal. And if we taking all the things at a time, then it is okay, fine enough to use as a amorphous material or cellulose nanofiber to utilize for the different application. that we have calculated the yield, and it is almost comparable whatever people have reported already in the bioresource and carbohydrate polymer. We are getting some 73% yield, whatever people have used the 69% after reprocessing. Though cellulose nanofiber has cellulose content in the particular raw material, we are getting its 40%, then we can come up with the 73% recovery of the 40%. That is very important. That is very important, whatever we are reporting like that. Let's start with that of the analysis for FTIR. Then FTIR main principle, whatever we are targeting to get the functional group analysis. Here, functional group in the cellulose means unmodified material. That is unmodified means raw fiber, where there is a lignin, where there is a hemicellulose, where there is a cellulose itself. From the lignin, that 1738 peak, this is related to carbonyl peak, and it is confirming that lignin is available. And after the cellulose fiber formation, after the acid treatment and the chemical treatment, we are getting a purified cellulose material. There is no at all that carbonyl peak, which confirm that a particular removal of the lignin. And cellulose nanofiber definitely is supposed to again confirm there is no lignin. Notwithstanding that to only the FTIR spectroscopy, but we have done with that of the ASTM analysis for this percentage of the hemicellulose, alpha cellulose, and percent lignin. Just I can confirm you, though I am claiming there is no lignin percentage, but as per chemical analysis concerns, I have seen it is 2.03% still lignin is there. But whatever our target application is there, this 2.03% is not too much high to hamper our application. So I'll be continuing with that of the particular things of the cellulose hemicellulose, the lignin content of this material. We have done the percent crystallinity calculation in the cellulose nanofiber. It is not cellulose nanocrystal. If it's cellulose nanocrystal, whatever we are getting for the cellulose nanocrystal, it is more than 95% of crystallinity. But cellulose nanofiber, it is crystallinity, we are getting 79%. After reprocessing cellulose, getting cellulose nanofiber, we are getting a reduction of the cellulose crystallinity 72%, because that whenever we are applying the ultrasonication speed, then it is breaking the cellulose fiber. As a result, what happened? It is the reduction of the crystallinity a little bit. That there are different methods. That whatever this time I am showing it here. This is the Seagull method for calculating the crystallinity. There are already another method. We have published some other paper where we have already calculated by the area method also. Almost both are similar. There is not too much of difference in the result, whatever in the case of the cellulose nanocrystal crystallinity. So morphology point of view, if you see, then you must be knowing, then there are different type of morphology characterization. Then somebody must be already teaching to you. It's atomic force microscope, transmission electron microscope, or your scanning electron microscope. But from the electron microscope point of view, just this is the different from the optical microscope. Here, electron as a scanner we are using. When you will be using electron as a scanner, when light as a scanner, then light wavelength is very, very high. Electron size is very, very less. So finer structure, you can get it with that of the APSM or ACM image. ACM and APSM, there is different field emission where cold plasma used to generate, it will not be heated up, so that resolution will be very, very high. If you go for the basically only ACM image, that it is the hot plasma, that heating will be there. That's why during the basically bombardment, that's why resolution is a little bit less. And we are getting whatever we are getting with the cellulose nanofiber, it is very finer like structure. And from the atomic force microscope, so let me just as it is related to your characterization things, just I'm trying to explain to you in this different aspect. What is atomic force microscope? Atomic force microscope, telling the mechanism of the atomic force microscope, please just try to realize one thing. One blind person wants to see an elephant. If he is touching to the total body, then it will be very huge. He will be giving the feedback, then that elephant is very, very big. And if he is taking the touching the tail, he will be telling elephant is very, very thin. So it is the feedback mechanism by cantilever, and we are getting the tapping type of things, and we will be getting the information. Based on the information, you will be getting many information like that. Either you can get a phase image, whether it is soft and hard, like blind man, whenever he will be using the stick, This whenever he is putting the stick, if it is going down, then he will be thinking there is a gadda, hey udar. Then if it is little high, then it will be, then he will be big cautious. And if it is plain, then you will be thinking it is plain surface. If it is getting the very hard surface, then that is the basically hard and soft. And topology and hard and soft segment, all the things you will be getting. Here, whatever we have used for the AFM as a tool for analyzing the thickness, that we have drop casted our material, and this is cellulose nanofiber. You can realize it. The cellulose nanofiber that we are getting the very, very fiber-like structure, and we are draw a line to how much thickness it is getting it. Then this is the type of things, thickness we are varying, and as a result, what happened that from the APSM point of view, we are getting the thickness is somewhere in 11.8 nanometer, but at AFM just we are getting somewhere just if you see it's maximum 4 nanometer to 5 nanometer itself. So as there is a difference in the process, that's why we are getting the different result. But you can do anything either of these, either APSM or atomic force microscope. Thermogravimetric analysis, then you must be knowing, just can you take 1 second? I'm feeling a little bit of... just switch on the fan. Okay. So let me start with that thermogravimetric analysis. Thermogravimetric analysis, I think somebody has already made a teaching to you. Its simple principle is that we will be getting the weight loss versus temperature, weight loss versus time. You can do a lot of things. Then what is the thermal stability? What is the initial degradation temperature? What is the maximum degradation temperature? What is the number of degradation? You will be getting all the things. So here, in the case of our cellulose nanomaterial, we are getting the it's a little bit of stabilized material after the extraction, because lignin, whatever it is there, it is creating problem because it will burn a little faster than that of the our material. So let's start with that of the particular material, how we can utilize this particular material for the advanced application. Preliminary, we have started this material, whether this material will be act as a reinforcing material or not. We have taken a simple things that for the proof of concept for the time being, but already we have developed the high-end application. I'll be telling from the slowly chronological way how and what way we have utilized it. And this is the things basically we have used as a template polymer, that is block copolymer thermoplastic elastomer. ACBS polymer we have taken, and we have added the CNF as a nanomaterial. And most important thing is that just filler loading, you try to realize filler loading, we have used very, very minimum quantity. 0.001, 0.005, 0.01, this is the basically maximum filler loading. Most of the cases you will be seeing in the literature, that is 4%, 2%, 3%, and where that is a PHR, and where we are getting is very, very minimum amount of material, because surface area, and if you're able to disperse it properly, you will be getting very good result. And first, we have used the malicanated grafted ACBS, because simple fundamental thing is that my material is highly hydrophilic in nature. So the material, whatever I will be using for reinforcement, there are supposed to be some connection point. The polar will dissolve polar, so polar will interact with polar, and non-polar will interact with the non-polar. So if it is polar and non-polar, the compatibility and dispersion will be the issue. So whatever we have used ACBS malicanated grafted material, so that malicanated grafting interaction will be there. Malicanated means it is a basically the polar part. So whatever it was the non-polar ACBS, it is a little bit polar, so that my material, which is highly polar, okay, that can be dispersed very easily. And we have used the unmodified also, and we have checked. I'll be showing you the result, then you can realize it. This is the mechanism, whether there is a reaction or not. First, let me explain to you, then I'll come back to the mechanism, then it will be very useful for you. Then you will be seeing it here, 0.00 and 0.005 pH of the cellulose nanofiber. It is giving huge mechanical improvement. It's very huge mechanical improvement. Whatever base material it was there somewhere in 15, we are getting somewhere in 27. The 98% Young modulus, 7% of tensile strength we are getting. And if you see the tensile strength, means unmodified cellulose, unmodified ACBS, whenever you are using, it is decreasing the tensile strength. whatever it was 15, now it is going down to the below 10. Though, so means that what I want to convey the message and take home message for you, polarity is very important. If polar interaction point is there, then only you will be getting the reinforcement, otherwise not. Here, that is the reason I have used the polar modified ACBS. Then what is the reason behind it? Just I'm trying to explain to you. This is the basically optimized FTR spectroscopy, and this FTR spectroscopy in this particular graph, that is A and B, what I want to show you, that in the rubber technology, there is one concept that is called the bound rubber or bound filler. So here, if our material is really interacting with that of the polymer matrix, filler is really interacting with the polymer matrix, then it will be some inseparable part will be there. What is the inseparable part? Then after the removal of all the cellulose material, that cellulose, whatever we are getting, still it has content 712 peak, means that what I am trying to tell you, that 712 peak is related to your carbonyl ester bond that is available in the maleic anhydride grafting. So after the oxidation of this particular raw material, still it is there, means there is a tethering reaction between the polymer and the filler. This is the reaction mechanism, whatever we have shown it here, that is the reason it is giving the reinforcement. So reinforcement mechanism I have told to you, there is a tethering reaction. This tethering reaction is very important. If it is not, mechanical property is supposed to increase a little bit. If there is only physical interaction, but it's supposed not to, almost somewhere in 100% interaction in increment supposed not to be there. And notwithstanding that, I have compared with that what I told you. This is again the case of the maleic anhydride grafted material with cipuolite. And frankly speaking, I have done this job. This particular paper we have published in Cellulose. Now, before that also we have published the similar type of job with ACBS by adding cipuolite clay and published in Polymer for Advanced Technologists, and we have seen it is requirement is almost 3 PHR. You see, it is U3 means cipuolite content is 3, and we are getting 105% young modulus increment 32 tensile strain. And the Ganguly et al., he has published it in the macromolecule, and you see they have used 4 PHR of chloride 20 clay they have used. And if you compare, we have used at 0.005 PHR. Try to realize. This is the things, just what I want to tell you, that minimum amount of also cellulose fiber is also easily, if you're able to disperse properly, then it will also give you that type of property increment, what is you will be getting with the 4 PHR of material. This is the microstructure. Then you see that the 0.005 PHR microstructure is very good. And after the tensile break of the sample, you will see this fiber-like structure it is generating in the broken part. Means it is given this mechanism that there is a fiber alignment, whatever it is there with the polymer. That's why it is giving the mechanical property improvement. We have done the your TM and APSM also, AFM also. This is giving that type of morphology. Notwithstanding that, till date we have not published this paper. Just taken at the polyurethane as a matrix. Then here, wherever it was the 0.005 PHR, here 0.03 PHR is giving mechanical property improvement, almost 300% young modulus increment at 200% young tensile strength improvement. So this material has the property to improve this mechanical property of the composite. So that was the things what I told you. Now just that we are working in a different direction also for how we can replace the carbon fiber material with this material. We are working, though I am not showing it to you because we are trying to go for the patent application of this particular material, the replacement of the carbon fiber. Now I'm going to in different direction. So why this material? Why not to material utilized for some other application for the biomedical application? Let's start with this particular things. What for the requirement of the biomedical application? Some active material you have to introduce there. If there is active material which has antimicrobial property or other property related to biocompatibility, then definitely we will be getting it. Cellulose nanofiber we are using, and along with the bioextract for fabricating sodium alginate-based multifunction composite, and we published it in the carbohydrate polymer. This is the combination of the material we have used: sodium alginate, cellulose nanofiber, sodium alginate, cellulose nanofiber combined. We have used distilled water, rice water, giloy water. Now, and mixture of rice water and giloy water. The simple things, just everybody is knowing. Rice water, you must be knowing during our beginning age. I can recall I am coming from very village area. Whenever there is a stomach upset, my dadi used to give it. You please take some giloy extract, or sometimes they used to tell thoda sa fan patla karke pee lena. So that's what I am trying to tell you, means it has some ingredient which is some important parameter to biomedical application. So giloy extract and rice extract, it has a lot many ingredient which is antimicrobial, anti-inflammable material is present in there. That was the things we are trying to get the advantage of this material along with our material, cellulose nanofiber. Not only cellulose nanofiber to make it dimensionally stable, we have used cellulose alginate to mechanical stability to utilize for the wound healing application. Let's start with that from microstructure point of view. That microstructure point of view, if you see, it's a rice water, so sodium alginate and CNF nanofiber combination, it is giving very good microstructure. Then this very good microstructure, because of the very good microstructure, stability will be very good. So this is the mechanical property: compression strength, rice water, sodium alginate, carbon, cellulose nanofiber. It is giving the very increment of the compressive strength. And compressive strength, then you are seeing it, cellulose nanofiber, sodium alginate, compressive strength. Modulus value also is very, very good. That we have tuning what is the amount of other things that is available in this particular paper. Then you can go through it, then you will be getting, and so what is the composition of this particular material. This 8 times mu modulus and 4 times tensile strength increment. And basically, so we are just going for the everything that there is a little bit decrement, 6 times of a young modulus increment, 2 times of the tensile strength increment. We have checked antibacterial property, and for your good information, just I'm telling you the combination of this material, it is giving very good antimicrobial property. And we have done with that other 3 different type of bacteria, and all 3 gram-positive, gram-negative bacteria both are giving the very good result with the combination of this thing. We have checked with colony count method. Yes, everything is as per whatever I have shown in the photograph. Similarly, it was showing that 3 bacteria, positive and gram-negative bacteria, is showing the very good result also with that of the sodium alginate, rice water, and the giloy water along with the CNF. So just I'm going to this next part, how and in what way we can utilize this material. For utilizing this material, my material is supposed to be antimicrobial, that I have done it. Easy to apply for the comfort, yes, we have done it also. Adherent property, as it is cellulose structure, adhesion property is there. Cost effective, definitely whatever we have used, as it is raw material is very, very cheap in nature, I can comment that it is a little bit cost effective. Minimum dressing charge changes, and I am hopeful that it can be done. I'll be showing it to you later on. Mechanical stability, I have shown it to you. Provide barrier to the external contaminants. Yes, it can do. Non-toxicity and biocompatibility. Yes, it is non-toxic, biocompatible. I will be again showing the biocompatibility test. Most important thing is that it is moist wound environment application. It is not stable till date, whatever we have developed. So we must have to think that what happened after 5 hours of inputting the water media, it is going to almost dissolve like that way. So we have to think something, some modification still needed to make a mechanically stable during its application point of view. So what we have done very interesting thing. We have developed a biopolyurethane coating on the particular material so that material property will enhance without deteriorating its microstructure, number 1, without deteriorating its basically property in terms of antibacterial property. All the things would remain same, only things mechanical property and solution stability, it was very good improvement. This is the chemistry that epoxidized linseed oil we have used, combination with the castor oil fatty acid. Then first we have done the epoxidation, followed by the IPDI, then polymer formation. This polymer has been coated with that of the your sponge material. Just I am not going through details of the chemistry. That is the castor oil fatty acid. Then we have used with that of the different tool to check whether there is a by NMR and FTR, whether there is a that type of information of confirmation of the polyurethane particular moiety is there or not. We have confirm it. Then finally, just coming to that particular things, which is most important from the technology point of view. Finally, we are coming to the particular things. That stability of this material, whether it is coming or not, we have to check it. That porosity and all the things that is coming exactly whatever it was there. Then we have done. Then let me check. This is the after the coating. This is the morphology. If you see, the morphology is very good, and it's almost a little bit similar to whatever we have shown it to earlier. There is no change too much. But one important thing is that mechanical property is going to increase a little bit. Then that of the earlier compressive strength is going to little bit increment, and cyclic strength is also 40% strength. We are getting the very good recoverable property. Most important thing, it is the things that whatever it was dissolved at 5 hours time. Now our material, this is our material after coating. Still, it is stable, and this is sponge-like structure. It is very stable. It is flexible. So, from user point of view, that it is very, very good to utilize as a spoon healing application. And we have checked different type of media, PBS, distilled water, double distilled water, all the things we have used, and we have seen our material property is very, very good in the moist environment also. So highly porous, highly stable, flexible material, which is a really requirement for the wound healing application. Notwithstanding that, definitely we have done the biocompatibility and cell viability. Means yes, it is very, very it's not too much reactive with the cell, whatever we have developed. Hemostatic compatibility and hemostatic performance. Again, we have checked. It is very compatible with the blood, and there is no problem with at all. Then we have check with the aquathermal irradiation or corrosion test with the mice model we have done, and we have checked different histopathology test after the coating. Then there is no too much of change in the histopathology section of the mice, and we can conclude this material, whatever we have developed, it has a very good application implementation area for the biomedical. Till date, we are working some other. We are not working till now in this particular direction. Rather, one group, they are taking this particular job to just go to the next stage, and I'm helping them as a co-inventor of this particular another project with them. So that as being a specialist in polymer, then again, my thought process, why not to utilize as a material for the as a mechanical application? So my thought process was to generate that what I told you, that it was showing some three-dimensional porous structure. Now I want to play with the porosity of this material. Earlier, porosity was in the macro. Now, porosity, if it is in nano, then some other property will be getting. Then we have published this material paper in the Materials and Design. It's one of the highest cited journal, highest cited paper. So that we are trying to develop the aerogel. First, let me explain what is aerogel. Aerogel is nothing but the gel plus air. So if we able to make a composite of air and your polymer matrix, then it will be aerogel. But there is a concept that aerogel, your pore size and pore distribution, and that pore supposed to be mesoporous range. Mesoporous range means it is 4 to 50 nanometer dimension. So the 90% means the pore supposed to be more than 80%, but for our case it is 98% basically pore. It is air, and it is 1 or 1.5% is only the gel, that is the polymer matrix. This is the schematic representation of the aerogel production. First, we used to do the gelation of the material, followed by directional freezing, then sublimation. After freezing, we used to go for the direct sublimation so that molecular architecture of whatever it is inside, it will remain same, then it will porous, and pore size, whatever you are getting for 2 to 50 nanometer range. And this is the beauty things that we will be playing around with the porosity and to get some other property to make it different application. So this is the different application we can use nanocellular reinforcement, then aerogel, and we are trying to develop a thermal insulating panel type of things where we can utilize the fragile packaging, space dust collection, super absorbent, oil spillage, all the things I'll be showing to you. Other structural application of cellulose, silica-based aerosol, you must be knowing that whatever liquid nitrogen container you are using, that's again there is a aerosol, that is silica aerosol. As there is a silica aerosol, thermal conductivity is very, very less, and we'll be explaining why thermal conductivity is very, very less. Let me come with that other research interest. We want to utilize this material for the building insulation in cloud. Means if you see, and in the winter and the summer, whatever heat is generating or outside coming, that if we are able to give a thermal insulating panel, then definitely it will give you the inside temperature will not come, and inside temperature will not go out, or outside temperature will not go inside. That is the things what you want to utilize it. And this is the another way you can utilize the cryogenic insulation, high temperature insulation. This is the flame. Then you see after putting its aerosol that your this flower, hibiscus flower, there is no problem with the things in the above the aerosol and how much stable it is. So research objective is to cost reduction, utilize the bioresources, and here that is the reason people have used the inorganic material, silica material, which is not flexible and all the things. Our material, our thought process, we are using cellulose as a nanomaterial for the aerosol synthesis. Let's start with the preparation process of the cellulose aerosol. Then we have used different solution process, and here we have taken the different concentration of the cellulose in the water. That's 0.7, 1, 1.2, 1.5, 1.75. We have checked the density versus porosity. You see porosity, just to try to realize, porosity we have started with 98.6 and we have ended up with 99.4. Then almost it is 4, something it is there only the material, and density, bulk density and theoretical density is again it is very, very less. Density is also very, very less. So this is the drying process we have utilized, that is the fridge drying process we have utilized, and after utilizing this particular things, we are getting the density 8 to 20 kg per centimeter cube, porosity 99.5% to 98.6%, and it is very strong because it is more than 1 kilo of the weight it can withstand. It is very flexible that we can put it in the basically 1 cup. And this is the extra-microtomo analysis that is a monolithic structure inside the material of the aerosol which remains same. And this is exomicrotomic. It is nothing but the CT scan that is called micro CT scan. In the micro CT scan, that will give you the architectural characteristics of the material. And for our case, the architectural symmetry is almost remain same. There is no crack, there is no void. Means this material is monolithic. Means uniform structure is there, and this uniform structure is which is very important if I want to use it in the space application or some other high-end application itself. So this is the microtomic analysis, X-ray microtomography analysis of this particular material. It is showing the 2-dimensional as well as 3-dimensional structure. Then you can see how the cellulose fiber, it is not generated by your software. It is the image of this material. Try to realize. It is not software in a simulated data. It is already scanning data of the original material. Porosity, we have checked. Porosity is very, very high. It's 1 weight percent and 1.7 weight percent. That porosity is very, very high, and it's a range of mesoporous range. And this is the APSM analysis. You have done it. I'm not going in details. And what I want to tell you that 1 weight percent of the cellulose contained, that it's 82% in the mesoporous range. And if you can correlate, the mesoporous range means 4 to 50 nanometer. Majority in the mesoporous range means then thermal conductivity is supposed to be very, very less. Then now that's I am comparing the thermal conductivity, then I will come back to the other mechanical part. Thermal conductivity of air, it is 25 milliwatt per meter Kelvin. And if we are able to just below air or above air, then it will be super thermal insulation. But 1 weight percent of cellulose nanofiber containing aerosol, whatever we are getting 25.50 milliwatt per meter Kelvin thermal conductivity. Now, just I'm trying to explain to you, why this is happening like that way. Now, if it is a mesoporous range, then what is the pore size? Then I have told to you, this is the pore size is somewhere in mesoporous range, 4 to 50 nanometer. Now, if you do have the idea, mean free path of your air, it is somewhere in 67 nanometer. Now, if you see, for thermal conductivity, that at least mean free path of air is really required to just transfer the heat from one part to another part. as you are getting the mean free path, void inside it, it is below the mean free path of the air, then air, whatever it was conducting the thermal conductivity, it is also not conducting. Only thing is that whatever it is giving the conductivity is the moiety is giving conductivity. That's why we are getting somewhere around air conductivity. It is pure aerogel of cellulose. I'm telling you, it is pure cellulose aerogel. Now we have checked the mechanical property, we have checked the cyclic mechanical property, whether it is very good or not. And 1% material, it's giving the very good stability than that of the other concentration of the material. This is the research part, what I have done and published. But thing is that what I want to tell you, there is a really requirement to improve the thermal conductivity. Decrement is really required. This is air, this is PU foam, this is the silica aerogel, and this is our material, whatever we have developed. There are different type of application in the cryogenic insulation. You can utilize it, body jacket, helmet, super thermal insulation, you can utilize it. This is the mechanism. Now, just we were not very happy to getting 25.6 milliwatt or meter Kelvin thermal conductivity. So we have started do some modification to get reduction of the thermal conductivity. Then we have taken rice to wheat straw. Then we have done pulping. I have told to you also. Then we have done the lyophilization with different medium, different condition. Then I'm not just interested with this thing. Rather, we have coated with that of the material by PLA. And we have added some other material. Just I'm telling you already, this is patented thing. Some part I'm trying to tell you, MTMS as a precursor, methyl siloxane as a precursor for making the PDMS. Means what I want to develop here, it is a composite type of hybrid type of aerogel we want to utilize or develop. Here, after you developing this thing, we are trying to just incorporate the coating on it to get a thermal conductivity, to check the thermal conductivity. And thermal conductivity, it was much lesser than whatever we have developed. And other things, whatever we have done, we have added the cipolite clay inside it to get the flammability reduction. Then material cellulose, you must be knowing, it's very, very flammable. So we have added some 3 pH of cipolite clay into the matrix so that we are getting that whatever digital image you are getting after the cipolite clay, UL 94 is visual rating we are getting, but we are just deteriorating a little bit of thermal conductivity. Instead of 25 milliwatt per meter Kelvin, we are getting somewhere a little bit higher thermal conductivity. So there are different potential applications in the space. Then we do have one collaboration with the German Aerospace Center. Recently he came and he have given a presentation. We are doing a collaboration related to aerospace application, aerogel, hybrid aerogel. They are too much interested with the hybrid aerogel because that silica aerogel, it is very, very, it is weight is little high than the silica, your cellulose-based aerogel. Flexible aerogel blanket already we have developed just all the things. So we are not showing all the details because as we have patented few of this particular research. Flexible aerogel blanket. Then this concept of aerogel force us not to utilize only the super thermal insulation, but also utilize in the different application. I think I'm not behind the time. Hello. Hello.
Okay.
Okay. Half an hour is available with me.
Yeah.
Okay.
Yes, sir, you can.
Okay. So the concept of aerogel, I was thinking, why not to utilize for the some other application? As this is the porous structure, means it can take the water or oil, means much higher quantity than its weight. So we have started digging that cellulose aerogel, which was it's very, very super hydrophilic in nature. We are targeting why not to make a super hydrophobic in nature. That there is very, very contradictory things. We are making a super hydrophilic material to a super hydrophobic material. If it is super hydrophobic, and definitely we have to generate a super oleophilic characteristics so that it can absorb the oil if there is a oil water mixture. So in a couple of slides, I will try to tell you how we can utilize our basic concept of cellulose aerogel for oil water separation by modification of this aerogel by super hydrophobic modification. Let's start with the oil spill cleanup problem that you must be knowing. There are oil spill. It is creating a problem to the marine environment as well as in the basically your industry. what they are just generating the oil with water that cannot be reutilized again. So oil separation is very much difficult for the oil water recovery in the small plant also and big plant also. They are trying to get that type of technology so that they can separate the oil from the oil water mixer. And problem related to this thing, you must be knowing, if there is oil spill in the ocean or any marine environment, then that life of the marine life, it will be disturbed tremendously. So our target was to develop the easy fabrication, low density porous material. It's supposed to be hydrophobic, reusability is supposed to be there, mechanical stability, low cost, and it's supposed to be very user friendly also. So there are so many things that we can utilize, but our thought process to utilize the aerogel material that can come up with a different application. The research lag and approach that whatever we are trying to delete, that our material, cellulose means material, means any cellulose-based paper or material aerogel, if you add water and oil, both the things, it will be going out. But our concept is like that. If it is blue color is water, then water will be repelling and oil will be going out. Definitely for the reason, we have to create an environment such that then it will be accepting the oil and repelling the water. And this type of structure, if you're able to generate, then you will be able to come up with a solution that it will be useful for the oil separation from the oil water mixer. Let's start with that of the different process, with that of the deposition of the things. Then first experimental process, whatever we have done, then we have added some PVA some material, polyvinyl alcohol material, to give it a little bit of mechanical stability aerogel, NFC PVA aerogel. And this is percentage wise, you see 0.05 pH we have added. So notwithstanding that, after that, definitely means you have to add something that's supposed to be super hydrophobic in nature. Means your after coating, that's supposed not to create any change in the morphology itself. Then what we have done, this is the basically schematic representation of possible interaction between the NFC and esterification of NFC PVA aerogel. So what happened? Sterile acid chloride. This is the sterile acid chloride we have generated in situ. The sterile acid chloride, which has an 18 number of carbon atom. Now this group is very, very active to the esterification reaction of the weight. As a result of it, what happened? We are getting the ester inside the material, and outside we are getting the basically only chain of the olefinic link. This olefinic link chain, it is really super hydrophobic, whatever super hydrophobic, and it is oleophilic because oil, it is again that type of similar characteristic. So oil will sit there, water will not sit there. As a result of, we are getting that type of analysis, we are property like that way. Chemistry point of view, we have tried to check it. What is the chemistry behind it? Okay, I'm not going through in details, but related to technology, I'm trying to tell you here how we have achieved almost 160-degree contact angle. Try to realize 160-degree contact angle, it is really super hydrophobic. Above 120, it is super hydrophobic. Okay, so when it is unmodified cellulose, then it is taking water and oil together, and modified cellulose aerogel, you see, it is taking the oil and water. We have added some pigment on it so that we can distinguish it, that it is not taking at all. It is, you see, it is rounded like anything. So this material can be utilized for the oil water separation. This is the basically mechanical point of view that's supposed to be very, very strong in enough. Then it is, you see, NFC, PVA, SSE, modified material, mechanical properties, very, very good. Then that of the other material, whatever unmodified material, so that mechanical it is strong. And after the addition of the modification, we are getting the 40 kPa to 59 kPa. Now, just see the video, then contact angle and your oil water separation, then you will be seeing it. Then whenever we are putting, immediately it is going out and it's unmodified material, it is taking water and oil. Then modified material is taking only oil. And we have used the basically some castor oil type of things with some pigment or some colorant so that we can distinguish this thing. You see, it is taking the oil. We have now stopped it here. We have checked the oil absorption capacity with this of the equation, and we have checked with toluene, hexane, ethanol, vacuum pump oil, chloroform, then linseed oil, diesel engine oil, water, CO water. We have seen. Then we are getting the chloroform as a one of the best material to absorb with this material. And reusability study whether this material can be utilized for many times. We have checked how many times we can do it. Then mechanics, this is the simple mechanical squeeze, we try to do it. Then here, just after the 15th cycle, if it is not modified, then capacity of absorption it is going down drastically by 20%. But after modification, they start modification after 15th cycle itself, almost some almost some 70% property retention still it is there. That is one of the important parameter that at least many times we can utilize it. So addition of PVA is increasing the weightability with reusability. Now, just we are going little bit of different aspect. That what I will show you this thing. This is the thing that we have used the technology for modifying the paper on it so that it will be going to only pass the oil, and as a membrane type of things, it will repel the water. This is the process we have adopted this technology. That this is the process that ferrichloride, maleic anhydride, then myristic acid we have added to the deep coating. Then I am showing it here that your contact angle, it's again come up with the almost 160 or more than 160 degree contact angle. This is the chemistry behind it. Why? Just I'm not going in details, but rather I want to show you the mechanism or basically things. What is important in the technology point of view. You see, we have added some material, that some carbon chalk dust we have added. It is unmodified one. It is taking the oil as water. It is taking the water, and you see what we want to tell it that here the material, modified material, it is self-cleaning and it is also hydrophobic also. You see, it is not attaching anything inside it. Then if there is any dark particle, then that can be removed by water itself, by throwing itself. Okay, there is no addition itself. Okay, now just I'm going to the this is the basically mechanism. This is the mechanism. If it is the unmodified sample, again, as there is a contact angle is very, very less, then it will adhere with that other material. But here, whatever the material it is will be taking as a ball type of things, it will roll and it will take the dart particle with that other material. And we have checked whether this material can be used many times. Then what we have done, that control material, that modified material with things. Then what we have done, we use the sand material, sandpaper to check it, abrasion it. After the abrasion also still its property of the contact angle, it has not changed too much. And we have checked the contact angle after its utilization, the different pH and different mesh, we have checked contact angle is almost same. Means after reusable and long duration of time utilization of the material, it can be utilized for the many times. Then just I'm trying to tell you here, this is the material. This is the material just we have used. This is our membrane. This is our membrane. Just we want, this is oil. Red color is oil. It is taking the oil, and here when we are adding the oil and water, then you see oil is going out. There is no water, but here just I'm going to a little bit high. Then you will be seeing it. It is getting oil and water. Both are things. It's passing wherever. In our case, you see, we are keep on adding. It is just going to the oil only. There is no water going just below this thing. Notwithstanding that, then we have checked the flux. That flux rate, it's very, very high, almost 500 liter per meter square per hour. And then we have checked, and after the efficiency of the things, we have also checked efficiency of the check. Another most important thing is that we have make a basically combination of the oil, water plus surfactant to make a colloid, and our system is able to break the colloidal system to break the oil and water separation. Here, this is the optical image of the solution before just separating. You see, after separation, there is very, very less amount of droplet. It is available when I have used the NX and water plus colloidal system. Then if this is the optical image of basically colloidal system, but after breaking it, you see there is very, very minor amount of water droplet. Means you can tell and clarity of the water after and before, then you will be getting it very clearly. So from that point of view, I can tell you that optical that our material, whatever we have developed, that it is very good to separate the oil water, not only the mixer condition, emulsion condition, but also in the normal condition itself. That already ONGC has taken this approach us to take this work. Already it is patented. And next, what I am trying to tell you, I'm going to a little bit of a different direction with cellulose. Now you can really realize the old material cellulose, it has different advanced application, what I'm trying to show you here. Next, I'll be telling to you different some coloration or color, little bit of color application I'll be telling you. As I am just, you must be knowing aesthetic value is very important. So here we are trying to develop a material which will give us the color with cellulose nanomaterial. Try to realize, have you ever realized that cellulose material will be giving you the color? That whatever green color, red color, the flower, all the things, or the plant, all the things, this is not the cellulose is giving color. There is either some pigment, either some dye, it has generated by the plant, that's why it is giving the color. But my case, whatever I'm trying to develop, that we will be developing the material which can give the structural color. So let's start with some background of this particular importance of color. You can't imagine the wall is black and white. I think in our age, when we used to see the TV, it was the black and white screen. We are very happy during the time. I think any person must not be very happy nowadays, black and white TV. And then it will not attract to the people to see the product if it is only black and white. The people will not appreciating that, people are not giving that thought process to purchase it also. So if color is beautiful, and that's why it is selling property, it will increase many folds. For any product, if you see, whatever it is inside, you don't know. But from the color point of view, from the printed point of view, you will be seeing, okay, it must be very good. So color is the important parameter. That color can help quickly to identify and understand important information as well as the retain its long term, but how color is added to the product. So there are different type of product of the color, you must be knowing. I do not want to go in details also, organic or inorganic color, synthetic or natural color, then global synthetic dye and pigment. There are so many problems you must be knowing if it is synthetic color, and there are so many problems to the biological as well as health hazard system. I'm not going in details, but one thing is that, important thing is that, then why not natural pigment? Then if you see that your hibiscus flower, it is red in color, then you can extract the pigment, that hibiscus, then to utilize in the different applications. That's why during your Rangoli or your indoor Holi, people used to tell, "Are color use kar lo jo bio color hai." Okay, people are using, that is good, but very, very costly. But our thing will be a little bit different. And if you see, but can you please correlate the two color of this two object? One is butterfly, moth butterfly. Another is basically it's apple. Apple color, whatever you are getting, this is called pigment. So what try to realize it, very listen to me very carefully. Then this is the pigmented color. And whatever your morphine butterfly structure, whatever you are getting, it is not at all pigmented structure or pigmented color. Rather, if you change the angle, then color will change. That is called the structural color. It is both are not same. This is due to the structure, and this is due to the pigmentation. So my thought process want to utilize the structural color mimication with our material. Let's start with that of the material, how it is to happen in the color. Either pigmented color, either structural color, or either bioluminescence. Then generally people color, whatever it will be reflecting, that reflected color you will be getting. I'm not going into details. I'm going to the details of that thing, how structural color will be helping us to utilize in different application, or high refractiveness particle, green color, circular, showing long range ordering structure, whatever it will be showing in the structural color, I'll be telling to you. So now, so what if we mimic nature and make structural color ourselves? And what if we could do it sustainably from the new renewable sources? Then structural color, I have told to you already that mostly we can use with the polysaccharide, we can use the protein, we can use other biological metabolites to get the structural color. But for our case, we'll be using cellulose as a material for the structural color. So from the structural color point of view, then definitely we can go up to the cellulose nanocrystal. After going to the cellulose nanocrystal, then cellulose nanocrystal has a specific structure that is called, the self-ordering structured material. The cellulose structure, this is the cellulose one. This is the cellulose crystal, another cellulose crystal, another cellulose crystal stacking like each other. This during stacking, it used to maintain particular stereochemistry. For this stereochemistry maintenance, then what happens? The self-assembly, it will, when there is a light bombardment, then what happens? It will reflect different color. That by presence, you will be getting that type of things, whatever we are regularly doing it with our lab. So this is what is happening like that way. This is isotopic, this is biphasic and cholesteric. In the cholesteric structure, if we able to change the pitch length, this is the P is equal to pitch length. If we change the pitch length, then color will change because color is totally dependent on the pitch length. So then what we have used with that of the sugarcane bagasse, we have developed the cellulose nanocrystal. The cellulose nanocrystal increasing the concentration so that we are getting the self-assembled material structure. Then step by step, then we have going for the first layer of PLA, then PCL, then added the cellulose nanocrystal material, then self-assembled structure. Then you will be seeing it's very intermediate. Interesting thing is that when we are doing adding the dopant, what is the dopant for us? Malic acid, citric acid, tartaric acid, absorbic acid, different type of acid. If we add, then this length, this piece length, whatever it was there, it will going to increase a little bit. This increment will help us to do it, the change in color that already we have done the with UV visual spectroscopy, there is change in color itself. So this color change, just we are coming up with a different type of color. You see, this is the after ascorbic acid adding, then we are getting very red in color. That is the orange-like color in the basically structure. This is very beautiful things. Then it can be utilized for the packaging application or aesthetic value that your material, our material is mechanically also stable, modular stability is very good. This is the structural and the morphology and compared in composite LBL means layered by layered assembly structure. This is the structure you see PLA, PCL in between cellulose with modified doping with different material. It is there and it is showing the different color itself. This is the mechanism how it is happening. That material, whenever you are adding in it, like your citric acid and your tartaric acid, then what happens? It will try to make a repulsive type of things, geometry of repulsive type of thing. As a repulsive introduction, then your cholesteric phase, whatever it was there, liquid crystalline phase, whatever is there, it will going to increase and it will change the color. And it has a very microbial activity also. So what we want to show it as a basically packaging application, because you have used tartaric acid, citric acid, it's a dopant. This dopant itself has a some antibacterial property. So this concept will help us to go to the next direction to why not to utilize this material as an anti-counterfeiting application. So now you must be knowing in the scenario of the counterfeiting of in 2020 that out of 100% fraud, that is 82% was anti-counterfeit, 12% smuggling, and 6% other things. So number of counterfeit incident reported in the top 5 sector. This is basically alcohol. That is a packaged alcohol. Instead of alcohol, it is something different, or they are using different undistilled alcohol. Then in the pharmaceutical product, there are so many different type of basically anti-counterfeiting packaging material people are using to sell it fraudulently. So if we able to generate an anti-counterfeiting coating application of our material, then that will be wonderful. And here, just we are trying to make an anti-counterfeiting solution and its mechanism itself. And for anti-counterfeiting property, there are 2 types of things. Either it is invisible, either it is visible. Invisible means itself you will not be seeing it, that immediate things you will not be seeing it. By particular tool, you will be getting that visible things that it is not fraud or it is fraud. The basic mechanism of anti-counterfeiting: product, process, incorporation, anti-counterfeiting technology, supply, sale, consumer, or configuring of the originality. Here, anti-counterfeiting property you have to generate either by hologram, either by giving some different type of coding, either by giving some different type of technology, anti-counterfeit technology, either if itself, that if you put a one seal, that is also anti-counterfeit. If you see it is open, then you suppose to purchase it, then it is not new. So this type of anti-counterfeiting, there are so many different type of anti-counterfeiting: watermark, thread, digital printing, then optical, print, epic, luminescent ink, so many things, machine readable ink, nanotechnology people have used. But our case, what we want to utilize, we want to utilize the cellulose as a nanomaterial to make it optically active, so that after printed, then it will be showing you that some feature that is not visible in the naked eye. Then we are trying to do it like that way, like it is UV white light, it will be showing UV light, it will be showing UV off, it will be showing like phosphorus type of things. Already it is available technology, people have already used it, but our case we will be using this particular technology by changing the pitch length with that of the material, by doing doping, whatever I have shown to you earlier. So why this material is important? This material is very important because bioresources, I'm not telling you, your schematic representation of HPMC, hydroxypropyl methyl cellulose. You must be knowing this hydroxypropyl methyl cellulose has been randomly used in the basically eye drop. And high-end eye drop, basically HPC, they used to use. And this HPC, it has a very good optical activity or optical property with different concentration. And we have checked with the chemistry first whether we are able to make a generation of the HPC. Then after the HPC, then what we have done, that what we have not shown it here due to the, it's basically we have apply for the patent, we have added some grafting which has some conjugated bond. If there is a conjugated bond, this will be optically active, it will be showing. And that is the result, just will be getting a little bit of optical activity in the UV range. This is different range. Then this you see, it's if it's normal things, there is no activity, and that whatever it is written, then it is visible with that some particular glass or something polarized optical microscope itself. This is the mechanism. Then you see anti-counterfeit anisotropic phase. Then you see, then after coating, then it is visible in the UV light. It is not visible in the normal light. Then already we have printed here, then UV visible light it is showing, and UV visible light again it is showing. So just I'm showing you the how you have already developed these things. This is simple ink. We have not done any extraordinary things with our research. We have taken the fountain pen, we have taken the ink, so whatever we have developed. Okay, you see it carefully, then it's very interesting. Then we are writing something IIT Roorkee confidential. You are not able to see it. Okay, it is not visible at all. Though some mark is there due to the impression, but after pressing, it will not. That impression will not be there. Now you see it's a normal naked eye. Naked eye, it is not visible, but in the UV, you see it is written IIT Roorkee. It is totally different. Whatever watermark is there, watermark is totally different, but whatever we are trying to show it here, it is totally different. And here we can change in the color of the IIT Roorkee, whatever it is written, based on the UV, whatever you are using, and based on our material, you can make it blue, either we can make it red. That what we are not showing it here to you. So there is this is the things that is very important. That material, whatever I was telling to you, it has a numerous different new application area and other potential applications, whatever I have not shown to you, that we can use the supercapacitor and battery. One of my group is working cosmetic, though I have worked a little bit, I have not shown to you due to time constraint. There we have plane and aircraft application. There are acoustic application. We have started working for the acoustic insulation also with the cellulose aerogel, and as well as the thermal insulation of the aerogel in the aircraft cabin. The car component already have shown a little bit. Solar panel thermal conductivity reduction, then we can use it layer there. Then CF multilayer film we have developed, oxygen barrier film we have developed, though I have not shown to you. Okay, now so many different type of application I can show you later on also if you are interested, because it is one of the vast area. Most important thing what I want to tell you, this material is very old, but if you see, I am telling to you very new application, and whatever people was showing that material, that it is biocompatible, it's very much abundantly available, and it has a life, it has a basically future, and that's why worldwide, if you see, there's so many people they are working with the cellulose nanomaterial, cellulose material for the different advanced applications. These are the few of the publications from this work. This is very few. Okay, I'm very much thankful to IIT Roorkee, ACRB for the financial support, Department of Science and Technology. Ministry of Education, MIF Foundation. I must have to appreciate the GSPS Fellowship from Japan. I must have to appreciate my students, those who have contributed a lot for getting that type of result. You must have seen that a huge result we have generated with the cellulose. And in India, you must have seen we are the only pioneer group related to cellulose application in the different advanced field, and we are getting enormous amount of fund in different private organizations. Like we have received recently one fund from Berger Paints. We have recently got from the fund from your John Deere India Limited. We are getting fund from the German government, that is called the Horizon 2020 fund. We have received also. I have not shown it here. Okay, thank you very much. Thank you for your attention. Though I was a little bit of high pitch and high speed, I hope you able to realize and understand whatever I was telling to you. For any point of time, if you see that you are not able to realize or understand, my phone number is available in the website. You can please connect with me, or if you do have any question, please feel free to ask. I'll try to answer you. Hello. Dr. Chatterjee, please. Hello.
Yes, sir. Yes, sir.
Please. If any question, please let me know.
Thank you so much, sir. If anyone has any question, please post it in the chat box. If anyone has any queries, please post it in the chat box.
If you do have any question, you can directly ask to me.
Participants, if you have any questions, please ask to sir.
Let them allow to ask this question without putting them in the chat box, because in chat box, it's required time to put it. I not mind it.
Is there anyone who has any queries? I don't think there are any questions, sir. Thank you so much. I request Piju sir to present the digital memento.
Thank you. Thank you very much.
Sir, please accept it from our end.
Thank you very much. Thank you.
We were honored to have you for our FTP. I think we can end our first session of the second day. The feedback link is already given in the chat box, and there is also the assignment. Please fill the both forms up and join sharply at 2 p.m. after lunch for the second session.
Okay, may I leave now?
Yes, sir.
Okay. Thank you, ma'am. Thank you.
Thank you, sir. Thank you so much, sir.
All the participants requested to kindly fill up the feedback link
Yes.
for the second day of session 1. And also you are requested to, the assignment has been provided to you in the chat box as well as in the WhatsApp group. So kindly fill it up from your end as soon as possible. And we will join sharply at 1:45 p.m. for the next sessions. Thank you all. Shubhandaka, please conclude.
Okay. Okay, thank you. You can, all the participants can leave now. See you after lunch.
I think it was disconnected. Hope I'm audible.
Yes, sir, you are audible.
Okay, okay. I'm going to share again the slide.
Yeah, yes, sir. Yes, yes.
Yes, here we are talking about the critical shear stress to compute how to compute the critical shear stress in case of the uniform cohesionless sediment. Shields is given the curve that is called the Shields curve. Using that sealed curve, you can compute the critical shear stress in dimensionless form. Then you can convert into the SI unit form. So here, how to compute the critical shear stress using the Shields curve. Shields curve given some plot between the dimensionless critical shear stress on the y-axis and x-axis it is having the particles Reynolds number. So that is the function of the mainly unknown factor is the particle size dA and its density rho s, and others is known. If you know these two, you can compute the value of R star. From that, you will get some point on the curve, and corresponding to that, you will get the dimensionless critical shear stress. So you have to use the curve again and again. So Brownlee in 1981, they have given the expression to compute the critical shear stress in place of using this Shields curve. We can use the expression directly to compute the critical shear stress. Here is the expression, that is the tau star Cm, that is the critical shear stress for cohesionless sediment, indicates this one tau star Cm. That is the dimensionless critical shear stress for cohesionless uniform sediment. That is equal to 0.22 multiplied by y plus 0.06 into 10 to power minus 7.7 y. Y can be defined here, y equal to square root of rho s minus rho into g into d50 power 3 divided by the rho nu ki, that is kinematic viscosity nu square whole power minus 0.6. That means here again, we have to know the value of the particle density and its size, d50 median size. If you know these two values, other values are known. So you can compute the value of y. Once you got the value of y, we can compute the critical shear stress in the dimensionless form. Then you can convert this into the dimension SI unit form. So in this way, you can compute the critical shear stress in case of the cohesionless uniform sediment. In case of the non-uniform sediment, that equation cannot be used. That equation is only restricted to the cohesionless uniform sediment. For the non-uniform sediment, the finite particles, what will happen in the case of non-uniform sediment? There is the mixing of the particles of different sizes is there. Different sizes of particles are there from finer to coarser particles. So when the flow will occur, may be the finer particles, because of the less weight, they may start moving earlier compared to the coarser particles, which is larger in the size. So that means the movement of one particular size of particle may start earlier compared to the other particle size. But that means both particles are present there. However, the starting movement may be for the particular particle. That is, there is the concept of that concept comes the unequal mobility. Unequal mobility, that means all the particles having the same size will not start moving at the same time. Particles having the different size may start the moving. That means that is called the unequal mobility concept in case of the non-uniform sediment. What happens if the particle size is less? It may hide behind the coarser particles, or it may expose on the surface of the coarser particles in between the gaps of the two or more coarser particles. While it is lying in the gap of the coarser particles and flow comes over it, then it may take the lighter particles, which is light in the weight. So that's why the sediment start moving, maybe the less having the particle which is having the less size compared to the coarser one. That is the unequal mobility in case of the non-uniform sediment. Now, coming to the cohesive sediment, how cohesive sediment will come into the picture? That is, on mixing of the cohesionless sediment with the cohesive sediment. Cohesive sediment, that is the having the cohesive property. Clay is having the cohesive sediment. So when this clay is mixed with the cohesionless sediment, that is like the sand, maybe the 40% of clay is there, 60% is sand is there. When mixing both, then it will become the cohesive mixture. Maybe 10% of clay is there, 90% gravel is there. So mixing of these two sediment and making the channel bed, it will become the cohesive channel bed. In the reality, cohesionless bed are mostly exist. However, cohesive sediment bed also found in the rivers. That means the erosion characteristics is governed by the particle size and its weight or density in case of the cohesionless sediment, but when it comes into the cohesive sediment, then erosion characteristics is governed by the some property of the cohesive, that is the physiochemical property of the cohesive sediment, because of the some particle bonding property with the other sediments or with the same sediment that is having the binding property, and it will affect the erosion or transport of the sediment. Here I am showing the some examples of the existing equation. This is for the cohesionless non-uniform sediment. Like Easier Zeroff in 1965, they have given the some expression for the sand gravel mixture. That is for the sand gravel mixture. In further 1980, Hayashi et al., they have given some different equations for the sand gravel mixtures. So these are the some equations already defined. Like 1965, 1980, 1982, all are for the sand gravel mixtures. But what will happen? Why the other expression is required? Because they may have the some certain experimental condition, Easier Zeroff, while the Hayashi have some other experimental conditions. They found for the different experimental condition, different results. So one result is not suitable for the another experiment. That's why they have given us some another expression according to their data. So these all are the for the cohesionless non-uniform sediment. Now coming to the cohesive sediment. Now cohesive sediment also some equations are existing for the different cohesive channel bed. You can see that Dune in 1959, they have given the expression for the channel bed which is having the clay and sand mixture. So it depends on the SVs, that is the vane shear strength, which is the clay percentage. Two parameters they have taken. However, if you see the Mitchell and Toff in 1996, they have taken the density, bulk density as the parameter for the clay mud mixture. Channel bed is made of the clay mud mixture. While Snowden and Wesley in 1961, they have given the expression depending on the clay percentage. PC is the clay percentage for the channel bed having the clay sand mixture. Similarly, D. Sutter et al. 2000, they have given the expression for the critical shear stress in terms of the W, that is the presence of the how much water content is there in the channel bed, and PC is the clay percentage for the clay sand mixture. Further, Ansari et al. 2007, they have taken the plasticity index, water content, and optimum water content along with the ER, that is the void ratio. Otiari and Jan, they have used the parameter clay percentage, ER is the void ratio, and UCS is the unconfined compressive strength. So that means different researchers have given for the different channel beds using the different parameters. Lot of parameter is there. However, there is no single equation is there that can define the critical shear stress for the cohesive sediment. So aim of the study here is to identify what are the main parameters that will affect the incipient motion, and then propose the equation to compute those either incipient motion condition at the critical shear stress. If the time permits, we will go for the sediment transport also. See here, the experimental study conducted in the laboratory of the hydraulic lab of the civil department, IIT Roorkee. For the experiment, 4 types of sediment is used. That is the clay, silt, sand, and gravel. These are having the size of 0.014, 0.062, 0.6, and 5.5. All are in mm. That is the median size of these sediment sizes. As the presence of clay is there, the clay is having the property, the liquid limit of this clay is 38.9, plastic limits 19.9. Elasticity index is the this minus this, that is the 19%. Maximum dry density obtained 1.7. Optimum moisture content 18%. Cohesion C value 28.59 Newton per meter square. Using these are the tests. Using this test, this method, these values are find out. And this is the what important clay mineralogy. Clay mineralogy, that is the using the X-ray diffraction test, got the clay mineralogy. This clay is having the collinite 78%, while the elite is 17%, and Mount Morenonite is 5%. Some other clay may have the other composition of the clay mineralogy. Here is the dominating is the collinite. Maybe the some other clay particles may have the dominancy of the Mount Morenonite. So in that case, the property may be slightly different from this clay. So also it is depending, that is the clay mineralogy is also play a role in binding nature. That is the, it will affect the transport of the sediment or erosion from the channel bed. So this study is suitable, while you have to mention the study in that study clay, what is the mineralogy of the clay. So 4 type of sediment is used. So using by mixing those sediments, 3 mixtures are made. One mixture is the clay silt gravel. One is the combination of the clay silt sand gravel. One is the clay silt sand mixture. 3 type of sediment mixture is there. One is the clay silt gravel mixture. One is the clay silt sand gravel mixture, and one is the clay silt sand. That is, you can see here in the second one, clay silt sand gravel, all 4 sediments are present. While in the first one, clay silt gravel is present, that is sand is not present. While in the third one, clay silt sand is present, that is gravel is not present. In the first one, sand is not present. In the last one, gravel is not present. While in the mid one, all 4 sediment is present. So we have made the different channel bed. That is 3 type of sediment mixture is there. Now for each sediment mixture, we varied the clay percentage. Clay percentage is varied in interval of 10%. That is the keeping that clay percentage 10, and the others, that is in the 90% other sediment is there. That is, suppose clay silt gravel mixture is there. In that mixture, when clay is 10%, then keeping the other 90% and in equal proportion. That is the 45 silt and 45 gravel. While clay is 20%, then silt and gravel both are having the 40%. When clay is 30%, then silt and gravel will have the 35 and 35%. When clay is 40%, then silt and gravel will have 30 and 30%. When clay is 50%, then silt and gravel will have 25 and 25%. So this is for the clay silt gravel mixture. While coming to the clay silt sand gravel mixture, when the clay is 10%, so remaining 90% is having the silt, sand, and gravel in equal proportion. That is the 30%, 30%, and 30% each one. While clay is 20%, then it will have approx 27, 27, 27. While clay is 30, then it is having 23, around 23 and 23. This is given in the round figure. Clay is having 40%, then silt, sand, and gravel will have each 20%. Similarly, when the clay is 50%, then silt, sand, and gravel will have each 17% around. Similarly, for the clay silt sand mixture, clay is varying and other sediment will have in the equal proportion in the remaining quantity. So these 3 sediment mixture is used. For each sediment mixture, we have computed the critical shear stress by varying the clay percentage. That is, what will be the impact of clay? What we have to see the impact of clay. When we have to see the impact of clay, then we have to vary the clay percentage. And only you are able to see the effect of the clay. What will be the effect of the clay on the incipient motion when the clay is varying in percentage wise. So this is the channel bed. This is the channel bed. You can see here. This is the, that is the from, you can see from this arrow line, up to here, this channel bed is there. Up to that channel bed is having the length of 16 meter. Length of 16 meter is there. While this is the working section. This section 6 meter is having the length of the working section from here to here. Cursor, I'm using the cursor, this one. Or I can use the pen also if, yeah. So this portion is the, let me change the color. Color, I can change the color, I think so. Yeah. I can change the color from here. So yeah, this is the length. That is the length of 6 meter. This is the working section. That means in this working section, whatever the sediment is there, that mixture is there, has to be made here. While this portion is the concrete portion, this portion is the concrete portion. That means total length is the 16 meter length is there, and out of 16 meter, this 6 meter length having the working section, while this 7 meter in the upstream and in the downstream, it is here the 3 meter is there in the downstream. So total is the 16 meter length is there. Water is coming from here. This is the tank, and water is connected here. Water pipe is connected here. It is coming into the here tank. From here, water is flowing in this direction. While water is flowing, after that, that means here the channel bed is there. That means that we have to make the channel bed using the sediment mixer, using some method. Then flow has to be allowed, and as the flow will allow, then it will erode the channel bed particles, and these particles will move from here. It will come into this tank. In this tank, we will install here some trap to trap the bed load. While for the suspended load, here we have attached one instrument here to take the sample of the suspended load. After this, water will come into this tank. Here, this tank can be used for knowing the volumetric discharge. That is how much discharge is there, which is flowing in the channel. This is called the volumetric tank for knowing the discharge. As water will come into this tank, one piezometer is attached with this tank to know how much water level, up to what water level is there in that tank. Then you know the area of the tank, you can compute the discharge. That is the volume into how much time it will take to come up to this level, and that time will be divided using this volume divided by the time, you can compute the discharge. So this is and one more thing is there, that is this is the railing, top railing. On the railing, you can put some measuring devices to measure the channel bed and flow depth. That is the water level as well as the channel bed. This jack, presence of the jack is there. With the help of, this is the automatic channel bed. That means you can tilt the channel using some electric button, and it will give how much slope is there on the channel bed. However, that slope is also computed using some method, and it is verified through how much slope is coming for the channel bed. So this channel having the length of 16 meter, and how much deep is there? This deep, 18 meter deep is there. It is having the 18 meter point, not 18 meter, 18 centimeter, that is 0.18 meter deep is there. While the width of the channel is 75. 75 is the width of the channel. And total depth is here from railing to the bed is 50 meter. From railing to the bed is 15 meter, 50 centimeter, while 18 centimeter is the here depth of the working section channel. So this is about the channel, that is the flume that is existed in the hydraulic laboratory of it. Yeah. Happy we wrote this one. Let me wrote this one. This is the channel bed. Now we're going to see first the preparation of the channel bed, then we will move further. Preparation of the channel bed. That is, in the working section, we have to pour the sediment. In the working section, that is empty one, we have to pour the sediment and we have to label the sediment. So how to prepare the channel bed? Initially, the required sediments were dried and weighted as per the proportion and mix them manually. That means the required sediment, that means what? Like we take the first case. In the first case, if you see the first case is the 10% of clay. For suppose consider this sediment only. Sediment mixture, clay, silt and gravel. For clay, silt and gravel, 10% of clay is there, silt 45%, gravel 45%. Suppose you are taking the quantity, suppose you are taking the quantity of 100 kg. So 100 kg, that means that 10 kg clay will be there, 45 kg silt will be there, and 45 kg gravel will be there. So taking this proportion and mixing them manually together. Then after mixing the dry materials, water is added to the sediment mixture and again it is mixed thoroughly. The mixed sediments, after mixing properly, the mixed sediment were covered with the polythene and left for the 24 hours for the uniform distribution of the moisture or water. So after 24 hours, the sediments again mixed once and they poured into the channel bed. So in the channel bed, we are making the channel bed in the 3 layers. Using the 3 layers, that is the, if you see here, the sediments were filled, the sediments mixture were filled in the test section and compacted in the 3 layers for preparation of the cohesive bed. That is, in the 3 layers, it is prepared. Using the dynamic compaction method. Now we will see how it is used. So that is the layer, that is the depth. Depth of the channel bed is 18 centimeter. In the first layer, suppose 7 centimeter is poured. 7 centimeter sediment mixture is poured there, and then it is compacted. It is compacted. It is compacted using the cylindrical roller that is having the weight of 400 Newton, and the sides of the channel is compacted using the hand rammer. That hand rammer is having the rectangular bottom. So to ensure the bonding among the different, when one layer is prepared, suppose 7 centimeter layer is prepared, then on the top surface, make it roughened so that when you pour the next layer on it, it will having the good grip from the both two sediment layers. So after compacting first layer, you pour the second layer. Similarly, second layer is also compacted using the compaction method and dynamic compaction method. Then after completion of the second layer, you pour the third layer. After completing all these 3 layers, the bed level was labeled. That is, upstream and downstream should be labeled as per the working section level. You can see here the preparation of the channel bed, that is the mixing of the sediment is there. This is the channel, the mixing of the sediment bed is there. After the mixing of sediment bed, it is poured into the channel. After pouring it, it is compacted using this roller, that is this compact roller and hand roller. After compacting, you can see the final stage of the bed. This is the final stage of the bed. That is in the upstream, concrete portion is there. The downstream also concrete portion is there. And in between, this working section is there where this is the mobile channel bed is there. We are studying the sediment transport in the mobile channel bed, alluvial channel bed, that is. So that's why this bed is prepared as a working section. You can see here also on this working section, that is on this channel, on this railings, this beam is supported. That is to measure the bed level. We will see that further also. So this is the preparation of the channel bed. This is the final form of the channel bed. Now some measurements are there, like how much slope is there, of the channel bed. So slope were measured using with the aid of the two containers, one in the upstream, one in the downstream. So in the upstream, we filled the container with the water. Then as per the slope, we left it for the 24 hours. So as per the slope, water is moved to the next one container. When it leveled, then there is no further moving of the water. So after that, we will see what is the vertical drop in the two containers. That vertical drop corresponding to how much horizontal distance is there. It will give the channel bed slope. Channel bed slope is also we can obtain from the automatic meter. So both are cross-checked, you get the value. Discharge measurement, already told discharge measurement, that is this tank is there, volumetric tank is there. So area is known to this tank. When water is coming to the tank, you can measure how much time it will take to go some water level. The piezometer will be attached. So it will give how much level is there. You can compute the volume and divided by the time, you will get the discharge. Also, the magnetometer is also attached in the pipeline. You get the flow discharge. So both are cross-verified. Bed load measurement. In the bed load measurement part is there. This is the trap. This is the trap which is located just after this is the tailgate. This is the tailgate. After the tailgate, the trap is located. Tailgate is to ensure how much to stable the flow discharge. How much flow discharge is flowing through that is some gap is there to at the end of to control over the channel depth, that tailgate is closed. So after the tailgate, this trap is there to trap the sediments which is coming in the form of the bed load. While the sediment which is coming in we are not talking about here the suspended load, only talking about the bed load right now. So using the trap, you can collect the bed load which is coming into this trap. For the suspended load, you can see here, this is the sampler, suspended load sampler. It's called the suspended load sampler. This suspended load sampler is located just before the tailgate. This is the tailgate. This is the tailgate. Before the tailgate, this suspended load sampler is attached. So it can be moved from the right to left or left to right across the channel. So while it is moving across the channel, one pipe is connected behind this sampler. That is when the water will cross this, then the water will go through the pipe and it will collect it in some tank. Tank may be the bucket also there. So water sample is collected in the bucket using this sampler. And this is moving across the channel bed. So this suspended load is measured using this one. So this suspended load was collected through a depth integrated sampler installed at the end of the flume just before the tailgate. Suspended sediment in the form of the sediment-laden water. That is when flow is there, the flow is having some sediment because of the mobile bed regions. So this is sediment-laden water through this sampler is collected in a 15-liter capacity of the bucket by traversing, that is moving across the channel. The collected sediment in the water, that is the sediment-laden water in the bucket, was then weighted. How much weight is there along with the bucket? It is weighted and left it for the 24 hours to settle down the sediment at the bottom of the bucket. Then the remaining portion of the water is removed and the whatever the sediment that is deposited in the bucket at the bottom is taken in some pan and it is wetted, and after that it is kept in the oven for dry. So that means we will be able to know how much sediment is there. So once you know how much dry sediment is there, then we can compute the concentration of the suspended sediment using that is dividing the dry weight of the sediment with the measured weight of the sediment laden water. This is method given by the Guardian Rangaraju 2000. That means you can compute the suspended sediment load, how much is there. Now the measurement of the bed and water surface profile. How to measure the bed surface and water surface. So bed surface can be measured using this bed profiler. In the bed profiler, it is having the three components. One is the profiler carriage, support beam, and the probe. This is the support beam. On this support beam, this profiler carriage is attached. So with this profiler carriage, this probe is attached. That means this probe is attached with this profiler carriage, and this profiler carriage is attached with the support beam. So this is connected with the, you can see this wire is connected with the computer system. Computer system, we have to set some distance. At what distance it has to take the measurement of the bed load. Suppose the interval is 50 centimeters. So it will touch the bed and take the reading, and again it will goes up and it will move horizontal 50 centimeter, and at the 50 centimeter it again take the reading, that is it will touch the bed. While it is touching the bed, the reading will be generated in the computer system. Again it will left the bed and it will go vertically up, then it will move horizontally. This profiler carriage will move horizontally 50 centimeter as per the instruction given set in the computer system. So in this way it will take the reading. So that means for taking the reading, probe is touch type of probe is there, which is touching the bed and taking the readings. Now the incipient motion, already we have defined the incipient motion. That means the incipient motion refers to the flow condition at which the motion of the sediment present in the channel bed begin to move. That means when the start of the movement of the sediment is there, corresponding to that flow condition, the incipient motion is called, that is the motion is called the incipient motion. So this is already told. Incipient motion in case of the non-uniform sediment is characterized by the unequal mobility of the particles present in the mixture. And this present study is focused on the coarser particle of the mixture. That is, suppose in the mixture, clay seed gravel is there. In this clay seed gravel, coarser particle is gravel 1. So you are focusing on the movement of the gravel particles only, while movement is under the influence of the clay and silt present. While the sediment mixture is there, clay, silt, sand, gravel, in that case, coarser particle is gravel particle. We are focusing on the movement of the gravel particle, while other particles also present. Similarly, in the mixture of clay, silt, sand, you are looking for the movement of the sand particles, while the presence of the clay and silt is there. Now let's see what is the procedure to find the incipient motion. Now the mixture is defined, channel bed is prepared. Now what will happen? Initially a low flow discharge was admitted in the flume. In the flume, low flow discharge was admitted in the flume, and uniform flow was maintained using the tailgate. When the low flow discharge was admitted, then in that case, discharge is that much, it is not able to erode the channel bed particles. Then what will happen? Then a small increment in the discharge was allowed. We have seen the channel bed is visibly from the sides. As in the sides, channel is having the glasses. In the sides, channel is having the glasses. So it is visible. The sediment is moving or not moving. how the flow is flowing. So initially we admitted the low discharge and see sediment is moving or not. Sediment is not moving. Then what we'll do again, increase a small increment in the discharge, and this sediment, and observe the sediment particles are moving or not. If not moving, then again we have to increase the flow discharge and examine the detachment of the particles. One stage will come when, that is the one flow condition will come, in that the detachment of the coarser particle started. So that condition, flow condition, is treated as the incipient motion. And in this flow condition, whatever the flow measurement is there, whatever the discharge is there, we measure the discharge, how much discharge is there using the volumetric tank, using the magnetometer. Then you measure the what is the water surface profile, that is what is the top surface of the water profile is there, and what is the bed surface profile is there. Along with that, also you will see how the top surface looks like. That is the visual observation method also adopted to cross verify the sediment transport for the incipient motion. So that means we started the flow in such a way that at one point sediment started to move. When the sediment started to move, sediment will come in the trap. You can see the trap also, sediments are coming. So at that flow condition, we set that flow condition. We will not further increase the flow condition, that flow. So at that, corresponding to that flow condition, we measure the different parameters like the discharge, water surface profile, bed surface profile. This is the picture of after the incipient motion, how the top surface of the bed looks like. How the top surface of the bed looks like. This is for the 20% of the clay. This is for the 30% of clay. This is for the 40% of clay. This is for the 50% of clay. And this is this is shown for the mixture of clay silt gravel mixture. Similarly, done for the other sediment mixture like the clay silt sand gravel and clay silt sand mixture also. So this is shown for the one mixture, clay silt gravel. This is for the 20%. This is for the 30%. This is for the 40%. This is for the 50%. So how the physical appearance is there? You can see here, as the mixture is having the clay, silt and gravel particles. 20% of clay is there. When the quantity is up to 20%, then that means if you see the original bed, then original bed is having the smooth top surface. A smooth top surface, that means the fine particles are there on the top surface. Fine particles here is the clay and silt. Fine particles are there on the top surface. And below that, the smooth top surface, there is the gravel particles are there. So when there is the clay percentage up to 20%, then the top surface of the thin layer, fine particles, clay and silt, disappeared along with the flow, and on the top surface, majority of the gravel particles are visible. So that is the physical appearance of the channel bed when the clay is up to 20%. When the clay is 30%, then we can see that there is a change in the appearance of the channel bed. You can see some here, all over the bed, gravel particles are not appeared, but along with the gravel particles, clay and silt finer particles are also present on the top surface. You can see some lines are created. Some lines are created. That is the removal of the finer particles in the form of the lines is there. So we have given the term line erosion pattern in case of the 30%. While moving to the 40%, you can see here erosion started at some point, and then it is spreading around it. The erosion is spreading around it, not all over the channel bed. Only at some particular places is there. That is it is like the mass erosion pattern. It is like the mass erosion pattern. Sediment eroded in the form of masses from one place. Similarly, for the 50% of clay also, we have seen the top surface. From the top surface, particles eroded in the form of the masses. While more deep is there in case of the 40%, less deep is there in case of the 50%. But in 40 and 50 both, cases, mass type of erosion was found. Why this is? Because here in case of the high clay percentage for 40 and 50%, the binding is much heavier. Binding is much heavier, so strength of the bed is much more. Because of the much more strength, particles eroded in the form of the lumps. While in case of the less clay percentage, final particles are removing because of the less bonding property with the sediment. This is the physical appearance. Now we see what is the impact. What is the impact of this clay particles? We have seen this Searles curve. We have seen earlier this Searles curve, that is for the cohesionless sediment. This is for the cohesionless sediment. If you use cohesionless sediment in place of the cohesive sediment, then we should get this curve. Data should come around this curve. But here the data, most of the data is above this line here, above this Searles curve. Above this curve, most of the data is lying. That means more critical shear stress is required. It simply indicates more critical shear stress is required, or more shear stress is required to move the sediment when there is the presence of clay. When there is the presence of clay, much more shear stress is required compared to the cohesionless sediment. This is the cohesionless sediment data curve, and cohesive data is overlapped on this cohesionless sediment curve, and for the comparison purpose. So we have seen much more shear stress is required to move the sediments in case of the cohesive sediment. You can see few data are close to this line. That is, few data are also below the line, while few data are close to the line. These belongs to the less percentage of clay. That is, when the clay is up to 20%, so data is lying around this line. When the clay is 10% or maybe less than the 10%, then the shear stress is required even less than the cohesionless sediment. Why this is? Because when less clay percentage is there, then in that case, binding strength is very less, and because of the less binding strength, these final particles start moving earlier. As it start moving earlier, so it disturbs the position of the coarser particle, and the coarser particle also start to move earlier when there is no presence of the finer particles. That's why some data are here below the cohesionless sediment curve. However, much of the data you can see here above the sediment. That is, when the clay percentage is 20 or higher, even for the 10, some data are higher above this line. So when the clay percentage is 20 or more than 20%, much more shear stress is required to move the sediment. That is the coarser. We are talking about the coarser sediment here. So for the comparison purpose, present acidity data along with the other acidity data also here fitted for the comparison purpose. And for all the studies, it was found that more shear stress is required under the influence of clay to start the movement of the coarser particles. Here now, after the comparison, we are going towards the development of the equation. So few parameters we have seen, like the clay percentage. We have plotted the clay percentage against the critical shear stress in the dimensionless form, and seen as the clay percentage increases, critical shear stress is also increases for all the three sediment mixture. This black is shown for the clay silt gravel, while this white boxes for the clay silt sand gravel mixture, while the dashed lines is for the clay silt sand mixtures. And for all the mixture, it is found that clearly seen that as the clay percentage below, it's going from 10 to 50%, critical shear stress is also increasing. Similarly, we have seen for the water content, As for most of the data, water content is, as the increase of the water content, there is the increase in the critical shear stress. However, we have seen also here the water content is increased, but there is the no increase in the critical shear stress. This is because of the not only the water content, but water content should be the optimal. If it's beyond the optimal, then it will decrease the critical shear stress. As the strength of the bed depending on the water content, but up to a limited extent. When the water content is optimal, that is, it increases the strength up to the optimal water content. After that, if water content is also added, then it will decrease the strength of the bed. That is, if you take the dry material, dry clay, you add the water, some water, it gives some strength. Again, increase the water content, it will give the more strength. But after a certain point, if you again add the water, it will become muddy. That is, the less strength will be there. That is the concept of the optimal water content. You have seen for the UCS also, unconfined compressive strength. We also found this is increases with the increase of the clay percentage. We have seen for the bulk density, we found this also increases with the increase of the clay content. So now, using these parameters, making the dimension analysis to get the expression, Say tau cc is that is the critical shear stress for the passive channel bed, passive sediment. Its function, taken the function of the critical shear stress for the cohesionless sediment. That is, suppose in the sediment mixture, you are using the sediment of clay silt and gravel. Then, if you take the average of this, you will get some median diameter. If you take that median diameter for the cohesionless sediment, then how much critical shear stress is required, that we can compute using the silt curve. So that is called the tau cm. So it is taken the function of the tau cm. PC, this is the PC is the percentage of the clay. It is taken here in the fraction. D50, that is the median diameter of the sand. It may be the for the gravel, that is for one particle. While dA is the for the mixture. dA is for the median diameter, for average median diameter for the mixer. Sigma g is the geometric standard deviation. Gamma b is this is the bulk density of the bed. Gamma W is the water content bulk density. That is the density of the water content. So using this parameters, making this into the dimensionless form, tau cc upon tau cm becomes the dimensionless function of the PC. PC is the dimensionless in the fraction clay percentage. Sigma cc is defined here. Sigma cc, that is this is the multiply of the size and geometric standard deviation divided by the size. So it will give the dimensionless form sigma cc. That is called the one parameter based on the geometric standard deviation and size. Then here the ratio of the gamma b upon gamma w, that is the bulk density of the bed divided by the density of the water. So it also having the dimensionless. So all are in the dimensionless form. Using this dimensionless form, we given the expression. These two expressions are given. This first one expression is for the mixture having the gravel particles. Mixture having the gravel particles. But the two mixture are having the gravel particles. One is the clay silt gravel mixture. One is the clay silt sand gravel mixture. While we have given the separate equation for the clay silt sand mixture, which is not having the gravel particles. As the gravel particles showing the significant different value compared to the having not gravel particles sediment mixture. So both this is the limit. One of the limitation of the study is that the clay percentage is up to 50%. So these two equations are given. We have plotted, observed, and compared computed value, not for the present study only, for other study also we have compared it. We are getting the 0.78 R square regression coefficient value. While for if we plot it for the individual sediment mixture, so for clay silt gravel, you will get the 0.85, while for the clay silt sand gravel, you will get the 0.84. We have seen for the clay gravel mixture of the Courtier and Janus, they have also studied but they use the different sediment mixers, but they use the clay particles. So for that, you will get the 0.78, and for the clay sand gravel, from the Cotier engine, you will get the 0.69. This is having the gravel particles. This is for the sediment mixture having the gravel particles, and this is for the sediment mixture without gravel particles. We're getting 0.71. However, for the present study, clay silt sand mixture, you will be getting the 0.82. This is the very good in case of the sediment transport. So that is about this presentation. This how I hope able to get something about the sediment transport issues, and what is the in simple motion, how the movement of the sediment will start, and how to get the expression based on the experimental study. So thank you. Thank you, sir.
Thank you so much, sir. Thank you all. I thank all the participants for patiently attending the program. Now, I request Nirottol sir to present our honorable speaker with the digital memento. Then we will take some questions if someone
Yes,
has
please.
any. Okay.
Yes, please.
Sir, please accept this.
Yeah, thank you. Thank you for this
Okay.
honor. I'm thankful to all the participants, all the students who came here to listen. This one patiently listening this. I am thankful to the organizers as well as the management. Thanks to the Greater Kolkata College of Engineering and Management that provides me the opportunity to share my work with the young minds. Thank you very much.
Yes. So, if anyone has any question now, does anyone have any inquiry? I don't think anyone has to say yes, furthermore. So,
Thank you. Yeah, no issue, guys.
yes, thank you, sir, so much.
Thank you, all of them again. Thank
Okay.
you.
And all the participants are requested to fill up the feedback form that is given in the chat box. The assignment link is also given. Please fill both the forms as soon as possible. It is given in the chat box.
So, ma'am, may I leave the session?
Yes, sir.
Yeah, thank you once again to the Greater Kolkata College of Engineering and Management. Thank you once again. Thank you.
Thank you, sir. All the participants are requested to check the feedback link and the assignment link that is given in the chat box. I think we can end our session now. Can we leave all? Can we all leave? Hello? Hello, am I audible? I think we can end our session right now.